Welcome friends. In the last two lectures on Routh Stability Criterion, we have gone through certain special cases of problem solving, and today again we are going to see another case which is the most wanted in the exam for solving Routh Stability Criterion based problems. So let us see. Today we are going to solve the problems based on this special case. Then we will consider few more situations in which you need to take special care to solve the problem, and you shall get certain problems to solve as homework. So we start with the next case. Let us quote the example as a problem. Test the following using Routh Stability Criterion. Using Routh Stability Criterion. So what is the characteristic polynomial over here? Q is equal to s power 6 plus 2s power 5 plus 8s raised to the power 4 plus 12s cube plus 10 square plus 16s plus 16 equal to 0. So let us draw the Routh array for this. So Routh array. So for this, the Routh array should be like this. We have the sixth power of s, so we have to write down the power of s like this: s power 6, power 5, s power 4, s cube, s square, s1, and s raised to the power 0. So we shall start filling up the values for this. So first two elements 1 and 2, s power 6, 1 and 2. So here I can write the second column as 8 and 12, third column as 20, and this is 20. Coefficient of a square is 20, so 20 and 16. Then the last element is 16, so other elements can be considered 0 like this. So let us start calculating from b1. So we have b1, b2, b3, b4 like this. So when you estimate for b1 equal to minus determinant of the matrix of 1 to 8, 12 divided by 2. So this should be equal to 8 into 2. So this one and this one. So 2 into 8 minus 1 into 12 divided by 2. So this should definitely come as 2. Then you get b2. So we have b2 over here. So this one and this one. So 2 into 20 minus 1 into 16 divided by 2. So this should be 40 minus 16 by 2. So 24 by 2 is 12. Similarly, you can go for b3. So when this element is 0, so this will be fed into b3, so that should be 16. So you can write b1 is 2, b2 is 12, and b3 is 16, and b4 is 0, like that. Now next is c1, c2, c3. From here, before we go for the coefficient of s cube, we see that these two, 12 and 16, have a factor that is 2 in common, so we can divide by 2 and make it little simpler, so it can become 1, 6 and 8. So this is the benefit, because this should be a polynomial. So in that case, when this becomes a polynomial, so the common term or common factor can be removed. So for s cube, we have c1, c2 and c3, like that, 1, 6 and 8. It will go like that: 1 into 12 minus 2 into 6 divided by 1, this is 0. c2 equals to 1. 2 into 8 divided by 1, this is again 0, and c3 equals to, this one will become exactly equal to this, so this becomes 0. So when the complete row is 0, we have a special case, and for such cases we have to define an auxiliary equation which is obtained by the row above the row of 0. So this is the row of 0, so this, the row above, will give the auxiliary equation. So then how we can find it? We have to write the auxiliary equation as a function of s as the coefficients. So here this is auxiliary equation for s power 4, so we write the coefficient 1 over here, 1, so this is 1 s power 4 plus 6 square plus 8 equal to 0. So this auxiliary equation will give us the pure imaginary roots of the characteristic equation of the system. So we'll find it out later. Let us find out the coefficients for the row of c1, c2, c3, which is now 0, but with little modification. How we can do it? We have to differentiate the auxiliary equation with respect to s. So this is d by ds of as. So this derivative will give us 4s cube plus 6 into 2, 12s, which will give us the coefficients for the 0 row. So here from these values I can determine that c1 equals to 4 and c2 equals to 12. So from here we can rewrite the Routh array like this. We can rewrite the Routh array like this. We have s power 6, s power 5, s power 4, s cube, s square, s power 1, s power 0. So we write again 1, 2, 8, 12, 2016 and 8, and 16 over here, 16 over here. So s4 has become 1, 6 and 8. Then these coefficients 4 and 12 will come here, 4 and 12. So this will replace the zeros. So this is the auxiliary equation, row for auxiliary equation, and this is the replacement for 0. So from here we can determine the further values. So we can find out 4 into 6 minus 1 into 12 by 4. So d1 equals to 4 into 6 minus 1 into 12 by 4 equals to 12 by 4 is 3. So we can write 3 over here. So this element is 0, so this becomes 8. And again you can find out that this power 1 is 3 into 12 minus 4 into 8. So here we get 12 into 3, 12 into 3 minus 4 into 8 divided by 3. So 36 minus 32 is 4 by 3. So we can write over here 4 by 3. So when this element is 0, so this 0 comes over here. So it becomes 0, and this is 0. So this element comes over here. So it becomes 8, like that. So from here we can find out certain values upon the Routh array. So first information is that we got the auxiliary equation, and by differentiating the auxiliary equation we got the coefficients which can be used to replace the 0 row, and from the auxiliary equation as equal to s power 4 plus 6 square plus 8 equal to 0, we can solve for the purely imaginary roots of the characteristic equation. So we get a square equal to, so this is same as a square whole square plus 6 square plus 8. So this becomes a quadratic equation a square. So that is minus b plus minus root b square, 6 square is 36, minus 4ac is 32 divided by 2a. So this will become equal to minus 3 plus minus 1. So therefore from here we can get s equal to plus minus j2 and s equal to plus minus j root 2. So we get the purely imaginary roots of the characteristic equation, and there is no sign change of the first column. So this is stable but marginally stable. So this we can write it in words like as there are pure imaginary roots, pure imaginary roots of the characteristic equation of the characteristic equation, and there is no sign change, and there is no sign change of the first column of the first column of the Routh array. Therefore the system is limitedly stable or marginally stable. So I write limitedly or marginally stable. So thus we have gone through two special cases in the study of Routh Stability Criterion. So what are those cases? First case one is the first element of the row is 0, so we can write that as the 0 pivot element, but the entire row is not all 0, but the entire row is not all 0. So this is the first case we have studied in the last lecture, and in today's lecture we have studied that when a row of all zeros, so The second case is very much important from examination point of view also. So if you see in the exam, there is definitely a problem on this, because you have to find out the imaginary roots of the system based on it. So we can consider another example, testing of certain roots, certain roots on the left half of certain point, certain roots on the left half of given point on a plane. So such problems should be taken care by shift of origin. So if I am telling you that you check whether say this is the S-plane, this is the S-plane, then you check whether certain roots are on the left of certain point, say -1. So what we have to do, we have to define a new plane in which you have to push the origin to -1. So to push the origin to -1, the new plane you should get in such a way that new plane, say escape plane, this is escape plane, should be such that this is equal to S+1. So all the values are, by adding +1, I am shifting all the values to the right by 1. So then if all the values are shifted to 1, so this -1 will shift to the origin, so -1 become origin. So suppose this point is -2 and -3, so this point will -2 will become -1 and -2 will become -2. So that is how we should perform the shift of origin to solve such problems. So I am giving a take home for you, just try it. So the characteristic equation is s cube plus 7s square plus 25s plus 39 equal to 0. So you have to check if all the roots of QS, check if all the roots of QS have real parts more negative than -1, have real parts more negative than -1, more negative than -1. So this is another problem which you need to solve by shift of origin. Another problem you can try by solving certain parameters of the system under the given condition of stability. So consider the system problem, consider the system, you have a system over here. Let it be k divided by s into s square plus s plus 1 into s plus 4 . Then we have certain input to it and certain output to it. So output is ys definitely, and input is the comparison between RS and a unity feedback signal of the output to the input, like this. So this is plus, this is minus. So for this system you have to determine the range of k for which the system is stable. So determine the range of k for which the system is stable. So you can try these problems, and in most of the situations we can handle the variety of problems by the knowledge we acquired in these 3 lectures. So this much is for today, and in the next lecture we shall consider learning of the root locus concepts. And if you find this lecture useful, please like the video and subscribe it if you have not done so far. Get the notification as soon as a new video is uploaded. In case you have any queries regarding this topic or any previous topic covered, you can always send me queries through this email, controlsystemsfaq@gmail.com. So friends, thank you for your patient listening.